Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernighan and Dennis Ritchie. At times, I add my own interpretation of the material from a historical perspective.
Chapter 3, Control Flow. The control flow statements of a language specify the order in which the computations are done. We have already met the most common control flow constructions of C in earlier examples. Here we will complete the set and be more precise about the ones discussed above. 3.1 Statements and Blocks. An expression such as x equals 0 or I++ or printf open paren ... close paren becomes a statement when it is followed by a semicolon, as in x equals 0 semicolon, I++ semicolon, printf open parentheses something, close parenthesis semicolon. In C, the semicolon is a statement terminator rather than a separator as it is in ALGOL-like languages. The braces, the curly braces, open curly brace and close curly brace, are used to group declarations and statements together into a compound statement or block so that they are syntactically equivalent to a single statement. The braces that actually surround the statements of a function are one obvious example. Braces around multiple statements after an if, else, while, or for are another. Variables can actually be declared inside any block. We will talk about this in Chapter 4. There is never a semicolon after the right curly brace that ends a block. Ah, C, how do I love thee? Let me count the ways. Quote by Dr. Chuck with homage to Elizabeth Barrett Browning. The humble semicolon is why spacing and line ends do not matter in C and C-like languages. It means that we, as programmers, can focus all of our white space and line ends on communicating our intent to humans. This freedom is not an excuse to write obtuse code or dense code. For example, see the obfuscated Perl contest, but instead, freedom to describe what we mean or use spacing to help us understand or maintain our code. We can take a quick look at how a few other C-like languages that came after C treat the semicolon. Java is just like C in that the semicolon terminates statements. Python treats the semicolon as a separator, like ALGOL, allowing more than one statement on a single line. But since Python treats the end of a line as a statement separator, you generally never use semicolon in Python. But for people like me who automatically add a semicolon when typing code too fast, at least Python ignores the few semicolons I mistakenly add to my code out of habit. JavaScript treats the semicolon as a separator, but since JavaScript ignores the end of the line, it's treated as white space. Semicolons are required when a block of code consists of more than one statement. When I write JavaScript, I meticulously include semicolons at the end of all statements because any good programmer can write C in any language. Back to the text. 3.2. If-else. The if-else statement is used to make decisions. Formally, the syntax is if parentheses expression parentheses, statement 1, else, statement 2, where the else part is optional. The expression in parentheses is evaluated. If it evaluates to true, that is, the expression has a non-zero value, statement 1 is done. If it is false, the expression is 0. And there's an else part, statement 2 is executed instead. Since an if simply tests the numeric value of the expression, certain coding shortcuts are possible. The most obvious is writing if, open parenthesis, expression, instead of if, open parenthesis, expression, not equal 0, close parenthesis. Sometimes this is natural and clear, other times it's cryptic. Because the else part of an if-else is optional, there is an ambiguity when an else is omitted from a nested if sequence. This is resolved the usual way. The else is associated with the closest previous elseless if. For example, if open parenthesis, n greater than 0, close parenthesis, if, open parenthesis, a greater than b, close parenthesis, z equals a, semicolon, else z equals b. The else with the z equals b goes with the inner if, as we have shown by the indentation in the above example. If that's not what you want, braces must be used to force the proper association. If n greater than 0, open curly brace, if a greater than b, z equals a, semicolon, close curly brace, else z equals b. This ambiguity is especially pernicious in situations like if, open parenthesis, n greater than 0, for, open parenthesis, I equals 0, semicolon, I less than n, semicolon, I plus plus, close parenthesis, if, open parenthesis, s sub I greater than 0, close parenthesis, open curly brace, printf, string, dot, 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 close parenthesis, semicolon, return, open parenthesis, I, close parenthesis, semicolon, close curly brace, else, and this is where it's wrong, printf, open parenthesis, error, n is 0, close parenthesis, semicolon. The indentation in the above example shows unequivocally what you want, but the compiler does not get the message and associates the else with the inner if. This bug can be very hard to find. By the way, notice that there is a semicolon after z equals a in if, open parenthesis, a greater than b, close parenthesis, z equals a, semicolon, else z equals b, semicolon. That is because grammatically a statement follows the if, and an expression like z equals a is always terminated by a semicolon. Section 3.3, else if. The construction if, open parenthesis, expression, close parenthesis, statement, else, blank, if, open parenthesis, expression, close parenthesis, statement, else, if, open parenthesis, expression, close parenthesis, statement, else statement occurs so often that it's worth a brief separate discussion. The sequence of ifs is the most general way of writing a multi-way decision. The expressions are evaluated in order. If any expression is true, the statement associated with it is executed, and this terminates the whole chain. The code for each statement is either a single statement or a group of statements in braces. The last else handles the none of the above or default case where none of the other conditions was satisfied. Sometimes there is no explicit action for the default. In that case, the trailing else statement can be omitted, or it may be used for error checking to catch an impossible condition. To illustrate three-way decision, here is a binary search function that decides if a particular value x occurs in the sorted array V. The elements of V must be in increasing order. The function returns the position, a number between 0 and n minus 1 if x occurs in V, n minus 1 if not. This sample code is on page 54. It is the first example on page 54 in the book. Binary, open parenthesis, x, comma, v, comma, n, close parenthesis. Int x, comma, v, open square bracket, close square bracket, comma, n, semicolon, open curly brace. Int low, comma, high, comma, mid, semicolon. Low equals 0, semicolon. High equals n minus 1, semicolon. While, open parenthesis, low less than or equal to high, close parenthesis, open curly brace. Mid equals open parenthesis, low plus high, close parenthesis, /2, semicolon. If, open parenthesis, x less than v sub mid, close parenthesis, high equals mid minus 1, semicolon. Else, if, open parenthesis, x greater than v sub mid, close parenthesis, low equals mid plus 1. Else, return, open parenthesis, mid, close parenthesis, semicolon, close curly brace, closing the while, and then return, open parenthesis, minus 1, close parenthesis, semicolon, close curly brace to end the function. The fundamental decision in this code is whether x is less than, greater than, or equal to the middle element v sub mid at each step. This is a natural for else if. I would note that in the above examples, the else and the if in C are two language constructs that are just being used idiomatically to construct a multi-way branch or else if pattern with indentation that captures the idiom. If we are pedantic about the indentation of the above sequence, we would be separating the else and if and indenting each succeeding block further as follows, with brackets or added for clarity. If, open parenthesis, expression, close parenthesis, open curly brace, statement, close curly brace, else, open curly brace, if, open parenthesis, expression, close parenthesis, open curly brace, statement, close curly brace, else, open curly brace, and now we're quite indented at this point, if, open parenthesis, expression, close parenthesis, open curly brace, statement, close curly brace, else, open curly brace, statement, close curly brace, close curly brace, close curly brace. Java and JavaScript keep the else and if as separate language elements and document their idiomatic usage and indentation just like C. But in Python, elif is a single keyword and a new language construct that achieves the same idiom as shown below. If, open parenthesis, expression, close parenthesis, colon, block. elif, open parenthesis, expression, close parenthesis, colon, block. elif, if elif, parenthesis, expression, parenthesis, colon, block, else, colon, block. The C, Java, JavaScript, and Python idioms thankfully look the same when the idiomatic indentation is used. Even Fortran 77 supports the else-if construct to implement multi-way logic. Section 3.4, switch. The switch statement is a special multi-way decision maker that tests whether an expression matches one of a number of constant values and branches accordingly. In Chapter 1, we wrote a program to count the occurrences of each digit, white space, and all other characters using a sequence of if-else, if-else. Here's the same program with a switch. This is the first example program on page 55. Pound include less than stdio.h. Main, open parenthesis, close parenthesis, open curly brace. Int c, comma I, comma n white, comma n other, comma n digit, open square bracket, 10, close square bracket, a 10 element array. N white equals n other equals 0. For I equals 0, I less than 10, I plus plus, n digit sub I equals 0. While parenthesis, parenthesis, C equals getchar, open paren, close paren, not equal EOF, close paren, switch, open parenthesis, C, close parenthesis, open curly brace. Case, quote 0, quote, colon, case, quote 1, quote, colon, case, quote 2, quote, colon, case, quote 3, quote, colon, case, quote 4, quote, colon, case, quote 5, quote, colon, case, quote 6, quote, colon, case, quote 7, quote, colon, case, quote 8, quote, colon, case, quote 9, quote, colon, n digit sub C minus quote 0, quote, close bracket, plus plus, break. Now that bit of code right there was to take all of 0 through 9 and guide it to the line of code that incremented the particular element of the n-digit array by 1. Continuing after the break, semicolon. Case, quote, space, quote, colon, case, quote, backslash n, quote, colon, case, quote, backslash t, quote, colon, n white, plus plus, semicolon, break. Default, colon, n other, plus plus, colon, break, semicolon, close curly brace. Print f, open parenthesis, double quote, digits equals, double quote, close parenthesis, semicolon. 4, open parent, I equals 0, I less than 10, I semicolon, I plus plus, close parenthesis. Printf, open parenthesis, percent, space, percent d, close double quote, comma, n digit sub I, close parenthesis, semicolon. Printf, quote, backslash n, white space equals, percent d, comma, other equals percent d, backslash n, double quote, comma, n white, comma, n other, close parenthesis, semicolon, close curly brace. The switch statement evaluates the integer expression in parentheses, in this case the character c, and compares its value simultaneously to all the cases. Each case must be labeled by an integer or character constant or constant expression. If a case matches the expression value, execution starts at that case. The case labeled default is executed if none of the other cases is satisfied. Default is optional. If it isn't there and none of the cases matches, no action at all takes place. Cases in default can occur in any order. Cases must all be different. The break statement causes an immediate exit from the switch. Because the cases serve as labels, after the code for one case is done, execution falls through to the next unless you take explicit action to escape. Break and return are the most common ways to leave a switch. A break statement can be used to force an immediate exit from a while, for, and do loops, as well as will be discussed later in this chapter. Falling through the cases is a mixed blessing. On the positive side, it allows multiple cases for a single action, as with blank tab or new line in this example. But it also implies that normally each case must end with a break to prevent falling through to the next. Falling through from one case to another is not robust, being prone to disintegration when the program is modified. With the exception of multiple labels for a single computation, fall-throughs should be used sparingly. As a matter of good form, put a break after the last case, in this case default, although it's logically unnecessary. Someday, when another case gets added at the end, this bit of defensive programming will save you. The switch statement. What is there to say? I think that the switch statement was added to C to compete with the earlier Fortran computed goto statement, or just to keep low-level assembly language programmers from switching into assembly language to implement the concept of a branch table. The authors spend most of the previous section apologizing for the switch statement, so you should perhaps take this as a hint and never use it. There are very few situations where a branch table outperforms a series of this if-then-else checks, and those are likely deep in a library or operating system code. Programmers should only use switch if they understand what a branch table is and why a branch table is more efficient for the particular bit of a program they're writing. Otherwise, just use else if and do the readers of your code a favor. 3.5 loops, while and for. We have already encountered the while and for loops. In while, open parenthesis, expression, close parenthesis, statement, the expression is evaluated. If it is non-zero, the statement is executed and the expression is reevaluated. This cycle continues until the expression becomes a zero, at which point execution resumes after the statement. The for statement, for, open parenthesis, expression 1, semicolon, expression 2, semicolon, expression 3, close parenthesis, statement is equivalent to expression 1, semicolon, while, open parenthesis, expression 2, close parenthesis, open curly brace, statement, expression 3, semicolon, close curly brace. Grammatically, the three components of the for are expressions. Most commonly, expression 1 and expression 3 are assignments or function calls, and expression 2 is a relational expression. Any of the three parts can be omitted, although the semicolons must remain. If expression 1 or expression 3 is left out, it is simply dropped from the expansion. If the test expression 2 is not present, it is taken as permanently true. So, the code for open parenthesis, semicolon, semicolon, close parenthesis, open curly brace, dot, 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 close curly brace is an infinite loop, presumably to be broken by some other means such as a break or a return. Whether to use while or for is largely a matter of taste. For example, in the code, while open parenthesis, C equals get char, open paren, close parenthesis, equal, quote, space, quote, or C equal, quote, backslash n, quote, or C equal, quote, backslash T, quote, close parenthesis, semicolon, skipping white characters, there is no initialization or reinitialization, so a while seems more natural. The for is clearly superior when there is simple initialization and reinitialization, since it keeps the loop control statements close together and visible at the top of the loop. This is the most obvious in for open paren I equals 0 semicolon I less than n semicolon I plus close paren, which is the C idiom for processing the first n elements of an array, the analog of a Fortran or PL1 do loop. The analogy is not perfect, however, since the limits of a for loop can be altered within the loop and the controlling variable I retains its value when the loop terminates for any reason. Because the components of the for are arbitrary expressions, for loops are not restricted to arithmetic progressions. Nonetheless, it is bad style to force unrelated computations into a for. It is best reserved for loop control operations. As a larger example, here is another version of the a to I function for converting a string to its numeric equivalent. This one is more general. It copes with optional leading white space and an optional plus or minus sign. Chapter 4 shows a to f, which does the same conversion for floating point numbers. The basic structure of the program reflects the form of the input. Skip white space if any, get the sign if any, get the integer part, and convert it. Each step does its part and leaves a clean slate for the next. The whole process terminates on the first character that would not be part of a number. This is the first example on page 58 of the textbook. A to I, open paren, s, close paren, which is going to convert s to an integer. Char, s, open square bracket, close square bracket, semicolon. Open curly brace, int I, comma n, comma sign, semicolon. For I equals 0, s sub I equal, quote, space, quote, or s sub I equals, quote, backslash n, quote, or s sub I equals, backslash, quote, backslash t, quote, semicolon, I plus, semicolon. Skip white space. This is a for loop with an empty loop body. Sign equals 1 semicolon. If s sub I equal plus or s sub I equal, quote minus quote, close parenthesis, sign equals, and here we use a ternary operator, open parenthesis s sub I plus equal, quote, plus quote, close parenthesis, question mark, 1 colon minus 1 semicolon. For open parenthesis n equals 0 semicolon, s sub I greater than or equal to, quote, 0 quote, and s sub I less than or equal to, quote, 9 quote, I plus, close parenthesis. N equals 10 times n plus s sub I minus, quote, 0 quote, semicolon. Return, open parenthesis, sign times n, close parenthesis, semicolon. Close curly brace to end the function. The advantages of keeping loop controls centralized are even more obvious when there are several nested loops. The following function is a shell sort for sorting an array of integers. The basic idea of the shell sort is that in early stages, far apart elements are compared rather than adjacent ones, as in simple interchange sorts. This tends to eliminate large amounts of disorder quickly, so later stages have less work to do. The interval between the compared elements is gradually decreased to 1, at which point the sort becomes effectively an adjacent interchange method. This sample code is the second example in page 58 of the textbook. Shell open parenthesis v comma n close parenthesis int v open square bracket close square bracket comma n semicolon open curly brace int gap comma I comma j comma temp. For open paren gap equals n divided by 2 semicolon gap greater than 0 semicolon gap slash equals 2 close parenthesis. For open parenthesis I equals gap semicolon I less than n I plus close parenthesis. For, and now we're 3 deep nested in the for loops. For open parenthesis j equals I minus gap semicolon j greater than or equal to 0 and v sub j greater than v sub j plus gap semicolon j minus equals gap close parenthesis open curly brace temp equals v sub j. V sub j equals v sub j plus gap semicolon v sub j plus gap equals temp semicolon. Just a swap of v and v sub j plus gap, v sub j and v sub j plus gap. Close curly brace, and that close the innermost for loop, and and then the next close curly brace closes the function. There are 3 nested loops. The outermost loop controls the gap between the compared elements, shrinking it from n over 2 by a factor of 2 each pass until it becomes 0. The middle loop compares each pair of elements that is separated by gap. The innermost loop reverses any elements that are out of order. Since gap is eventually reduced to 1, all elements are eventually ordered correctly. Note that the generality of the for makes the outer loop fit the same form as the others, even though it is not an arithmetic progression. One final C operator is the comma, which most often finds use in the for statement. A pair of expressions separated by a comma is evaluated left to right, and the type and value of the result are the type and value of the right operand. Thus, in a for statement, it is possible to place multiple expressions in the various parts. For example, to process 2 parallel indices. This is illustrated in the function reverse, which reverses the function string in place. This code is from page 59 of the textbook, and it is the first example on page 59. Pound include less than string.h greater than. Reverse open paren s close paren. Char s open square bracket close square bracket semicolon. Open curly brace. Int c comma I comma j. For open parenthesis I equals 0 comma j equals strlen sub s minus 1 semicolon. I less than j semicolon. I plus plus comma j minus minus close parenthesis open curly brace. C equals s sub I equals s sub j semicolon, s sub j equals c semicolon, close curly brace to end the function. The commas that separate the function arguments, variables, declarations, etc., are not comma operators and do not guarantee left to right evaluation. Section 3.6, loops, do while. The while and for loops share the desirable attribute of testing the termination condition at the top rather than at the bottom, as we discussed in Chapter 1. The third loop in C, the do while, tests at the bottom after making each pass through the loop body. The body is always executed at least once. The syntax is as follows. Do statement while open parenthesis expression close parenthesis semicolon. The statement is executed, then the expression is evaluated. If it is true, statement is evaluated again, and so on. If the expression becomes false, the loop terminates. As might be expected, do while is much less used than while and for, accounting perhaps 5% of all loops. Nonetheless, it is from time to time valuable as in the following function I to A, which converts a number to a character string, the inverse of A to I. The job is slightly more complicated than it might be thought at first. because the easy methods of generating the digits generate them in the wrong order. We've chosen to generate the string backwards and then reverse it. This is the first sample code on page 60 of the textbook. I to A, open parenthesis, n comma s, close parenthesis. Char, s, open square bracket, close square bracket, semicolon. Int, n, semicolon. Open curly brace. Int, I, comma, sign, semicolon. If, open parenthesis, sign equals n, close parenthesis, less than 0, close parenthesis, n equals minus n semicolon. That's a bit of a complex if, I would say there. It has an assignment statement that both copies n into sign and then evaluates as to whether or not it's less than 0. The n or sign is less than 0 because it's a side effect assignment statement with a residual value. But the net result is sign contains n, and then it's negated. Then n is made positive. So, continuing. I equals 0, semicolon. Do, open curly brace, s sub I plus plus equals n modulo 10 plus, quote, 0, quote, semicolon. Close curly brace, while, parenthesis, n slash equals 10, close parenthesis, greater than 0, close parenthesis, semicolon. If, open parenthesis, sign less than 0, close parenthesis, s sub I plus plus equals, quote, dash, quote, or minus sign, semicolon. S sub I equals, quote, slash 0, quote, semicolon, in a sense to terminate the string. And then we call the function reverse, open parenthesis, s, close parenthesis, semicolon, close curly brace. The do while is necessary, or at least convenient, since at least one character must be installed in the array s regardless of the value of n. We have also used braces around the single statement that makes up the body of the do while, even though they are unnecessary, so the hasty reader will not mistake the while part for the beginning of a while loop. I would note that it's important for any language to provide top-tested loops and bottom-tested loops. But don't feel bad if you write code for years and never feel like a bottom-tested loop is the right way to solve a problem you're facing. It is usually rare to write a loop that you insist will run once regardless of its input data. Section 3.7, break. It is sometimes convenient to be able to control loop exits other than by testing at the top or the bottom. The break statement provides an early exit from a for, while, or do, just as it does from the switch statement. A break statement causes the innermost enclosing loop or switch to be exited immediately. The following program removes trailing blanks and tabs from the end of each line of input using a break to exit from a loop when the rightmost character is non-blank, non-tab is found. This example code is on page 61 of the textbook, and it is the first example on that page. Pound include less than stdio.h, pound define max line 1000, main, open parenthesis, close parenthesis, open curly brace, int, n, semicolon, char, line, open bracket, max line, close bracket, semicolon. While, open paren, n equals get line, open paren, line, comma, max line, close paren, greater than 0, close paren, open curly brace. While, open parenthesis, minus n greater than or equal to 0, close parenthesis. If, open parenthesis, line sub n not equal quote, space, quote, and line sub n not equal, quote, backslash t, quote, and line sub n not equal, quote, backslash n, quote, close parenthesis, break. Line sub n plus 1 equals, quote, backslash 0, quote, semicolon, printf, double quote, %s, backslash n, double quote, comma, line, close parenthesis, semicolon. Close curly brace to end the while, and then close curly brace to end the main. Get line returns the length of the line. The inner while loop starts at the last character of a line. Recall that --n decrements n before using the value and scans backward looking for the first character that is not a blank tab or new line. The loop is broken when 1 is found or when n becomes negative, that is, when the entire line has been scanned. You should verify that this is the correct behavior even when the line contains only whitespace characters. An alternative to break is to put the testing in the loop itself. While, open parenthesis, n equals getLine, open parenthesis, line, comma, max line, close parenthesis, greater than 0, close parenthesis, open curly brace. While, open paren, --n greater than or equal to 0, and, open paren, line sub n equal, quote space, quote, or line sub n equals, quote, \t, quote, or line sub n equals, quote, \n, quote, close paren, semicolon, ... close curly brace. This is inferior to the previous version because the test is harder to understand. Tests which require a mixture of and, or, not, and parentheses should generally be avoided. 3.8 Continue. The continue statement is related to break, but less often used. It causes the next iteration of the enclosing loop, for, while, or do, to begin. In the while and do, this means that the test part is executed immediately. In the for, control passes to the reinitialization step. By the way, continue applies only to loops, not to switch. A continue inside a switch statement inside of a loop causes the next loop iteration. As an example, this fragment processes only positive elements in the array A. Negative values are skipped. For, open paren, I equals 0, semicolon, I less than n, semicolon, I plus plus, close paren, open curly brace. If, open paren, A sub I less than 0, close paren, continue. This line skips the negative elements, and then the rest of the body of the loop, ... will run only for the positive elements of the loop, and the loop finishes with a closed curly brace. The continue statement is often used when part of the loop that follows is complicated, so that reversing a test and indenting another level would nest the program too deeply. It's time for a bit of an aside. Now that we have seen the break and continue language structures in C that also have made it into C-like languages and learned about middle-tested loops, it is time to revisit the structured programming debate and the need for priming operations when a program must process all data until it finishes and still handle the there is no data at all situation. In the previous chapter, the author somewhat skirted the issue by using a top-tested while loop and a side effect statement with residual value that was compared to EOF to decide when to exit the loop. Int C colon, while, open parenthesis, C equals getChar, open paren, close parenthesis, not equal EOF, close parenthesis, open curly brace, process your data, close curly brace. And just for fun, now that we do know about the for loop, let's rewrite this loop as a for loop to make sure we really understand how for loops work. Int C semicolon, for, open paren, C equals getChar, open paren, close paren, semicolon, C not equal EOF, semicolon, C equals getChar, open paren, close paren, curly brace, process your data, close curly brace for the for loop. Now you will almost never see a read all characters until EOF written this way because it is not the way K&R told us. K&R told us to use a while loop for this. But the for loop formulation is probably clearer to many than the while formulation, especially to a reader who is not familiar with the assignment side effect idiom commonly used in C. In particular, the for formulation does not require that the assignment statement has a residual value of the value that was assigned. The first part of the for is a priming read. The second part of the for is a top-tested exit criteria that works both for no data and after all data has been read and processed. And the third part of the for is done at the bottom of the loop to advance to the next character or encounter EOF before going back to the top and doing the loop test. The call to getChar is done twice in the for formulation of the read all available data loop. And while we don't like to repeat ourselves in code, if it is a small and obvious bit of code, perhaps this code is more clear with a bit of repetition. So, with all this as background, you can take this page of the document and sit down with a friend at a coffee shop and debate as long as you like about which is the better formulation for the read all available data. But if at that coffee shop you ask Dr. Chuck's opinion, neither of these is ideal, because in the real world we build data-oriented loops that usually do a lot more than get one character from standard input. My formulation of a data loop will upset the structured programming purists and probably upset Kernighan and Ritchie as well. But I write code in the real world, so here is my version. Int C semicolon. While open paren 1 close paren open curly brace, C equals getchar. If open paren C double equals EOF close paren break. Process your data, and then close curly brace to end the loop. And if I wanted to skip blanks and new lines, I could use both break and continue, further angering the structured programming purists. Int C semicolon. While open parenthesis 1 close parenthesis open curly brace C equals getchar open parenthesis close parenthesis semicolon. If open parenthesis C equal EOF close parenthesis break. If open parenthesis C equal quote space quote or C equal quote backslash end quote close parenthesis continue, then process your data close parenthesis. I use this middle tested approach because usually the data I am processing is coming from a more complex source than the keyboard, and I don't want a function with 2 to 3 parameters stuck inside of a side effect statement in a while test. And also sometimes you want an exit loop not just based on the return value from the function, but instead based on the complex structure that came back from the function itself. As these data processing loops get more complex, the middle tested loop is a tried and true pattern. Even Kernighan and Ritchie point out its benefits above. And with that, I have now triggered endless coffee shop conversations about the best way to write a data handling loop. Section 3.9, Go-Tos and Labels. C provides the infinitely abusable go-to statement and labels to branch to. Formally, the go-to is never necessary, and in practice, it is almost always easy to write code without it. We have not used go-to in this book. Nevertheless, we will suggest a few situations where go-tos might find a place. The most common use is to abandon processing in some deeply nested structure, such as breaking out of 2 loops at once. The break statement cannot be used directly since it leaves only the most innermost loop. Thus, for open parenthesis, close parenthesis, for open parenthesis, close parenthesis, open curly brace, do some stuff. If open parenthesis, disaster, close parenthesis, go to error, semicolon, close curly brace, and then error, colon, and then clean up the mess. This organization is handy if the error handling code is non-trivial and if errors can occur in several places. A label has the same form as a variable name and is followed by a colon. It can be attached to any statement in the same function as the go-to. Another example, consider the possibility of finding the first negative element in a 2-dimensional array. Multi-dimensional arrays are discussed in Chapter 5. One possibility is for open parenthesis I equals 0 semicolon I less than n semicolon I plus plus close parenthesis, for open parenthesis j equals 0 semicolon j less than m semicolon j plus plus close parenthesis, if open parenthesis v sub I sub j less than 0 close parenthesis go to found. Otherwise, and then you handle and you keep going. And then found colon is where it comes to jumps to. Code involving a go-to can always be written without one, but though perhaps at the price of somewhat repeated tests or an extra variable. For example, the array search becomes found equals 0. For open parenthesis I equals 0 semicolon I less than N, ampersand, ampersand, exclamation, found, semicolon, I plus plus. For, open parenthesis, J equals 0, semicolon, J less than M, ampersand, ampersand, exclamation, found, semicolon, J plus plus. Found equals V sub I sub J less than 0. If found, continue, else not found. Although we are not dogmatic about the matter, it does seem that go-to statements should be used sparingly, if at all. I would add, before we leave control flow, I need to say that I agree with structured programming experts as well as Kernighan and Ritchie in that the go-to is universally a bad idea. There are a lot of little details that make them a real problem. Things like how the stack works in function calls and how code blocks happen and patching the stack up correctly when a go-to happens in the middle of a deeply nested mess. You might be tempted to use a go-to when you want to exit multiple nested loops in a single statement. Break and continue only exit the innermost loop. The authors use this example above, but are quite lukewarm when describing it as the use of go-to. Usually, if your problem is that complex, putting things in a function and using return or adding a few if statements is a better choice. The Dr. Chuck middle-tested loop data processing solves this because the loop is always the innermost loop. Also, as new languages were built, the concept of exceptions became part of language design and was a by far more elegant solution to a path of some deeply nested code that just needs to get out. So most of the time, you think that go-to might be a good idea, you should lean towards a throw-catch pattern to make your intention clear. It is one of the reasons why we prefer languages like Java or Python over C when writing general-purpose code.
This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. The book is copyright all rights reserved by AT&T, but is being used in this work under fair use because of the book's historical and scholarly significance, its lack of ability, and lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as a computer science evolved from a hardware-first vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn the C programming language because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications.